All right, let's take a look at the sketching polynomials with the end behavior. First, we're going to find some x-intercepts and y-intercepts, and then the degree, and look up the end behavior in order to sketch it. Now, these are sketches, they're not graphs, so they do not have to be perfect. We do not need to make sure these match with whatever Desmos would graph it as. So first, let's look at the zeros. Those are x-intercepts, remember. All right, same as x-intercepts. All right, so where does it cross here? Since it's already in this factored form, you just need to look at where do each of these equal 0. So it's actually nice and easy since each of these is already factored. All right, so we're solving each one of these, and you don't really need to write this part out, but that's how you're getting the answer. So you can probably look at this and see, oh, well, x equals 2 is the answer because 2 minus 2 is 0. Same thing here, we could probably get x equals 4 and x equals -1 as our answers without really writing this out. So it's fine just to write those three numbers and then go ahead and graph them. X is -1, +2, and +4. Our y-intercept is the value we get if we plug in 0 for each of these. F of 0, and we're finding out where x equals 0. So where on the y-axis would there be a point? So we get, let's see here, -2, 0 minus 2 is -2, times -4, times +1. So our y-intercept will be -2 times -4 times +1, which equals 8. So y equals 8. And that would be right up here on the y-axis at +8. Okay, so those were the same steps we did with quadratics. We're just doing it now with a cubic function. Now I know this is a cubic function because I have 3 x values. 1, 2, 3. So I know if I multiplied all these factors together, I'd probably get something that would look like this. X to the third plus a bunch of other stuff behind it. So because the highest exponent is 3, that's what the degree is. And this is important because that lets us know the general shape. We know that the shape of an x to the third cubic looks something like this from our practice. In general, that's what it looks like. You could also say it looks more like, let's see here, maybe this, right? Where it crosses the x-axis 3 times. And that's why we have 3 dots here, because we know with to the third function, it will cross 3 times. The important part here is that we know that the end behavior right here, on the left side, it's going to go to -infinity. And on the right-hand side, it's going to go to +infinity. We need to know that so we start our graph at the right place. So I know, because of that my graph should start somewhere down here and go this way, and it should end going this way. Just like this graph goes down on the left and up on the right, so will this graph because they're both x to the third. And the middle is going to be different, but the end behavior is the same. And the proper way to write this out we'd say as x gets closer to +infinity, f of x approaches infinity. Right? That's right here on the right-hand side. As this x gets bigger, so does this f of x. And same thing on the other side, we have as x approaches -infinity, meaning as we go to the left on the graph, the y's, or the f of x's, will get smaller. They'll go to -infinity, right? They'll be down here. As we go this way, the y values, or f of x values, get smaller. And then from here, it's just estimating and sketching a graph. It doesn't have to be perfect, right? But we have to go through these points that we have here. So we have, I'm going to go through here, 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 and then end right here. And that would be a good enough sketch. And it could be different for other people, that they could make it, go down a little bit further or just very small right here. It doesn't really matter. We'll get into these parts in a little bit, but for now we're just worrying about the end behavior, x-intercepts, and y-intercepts. All right, so let's take a look at number 2. Here. Okay, we do have a negative in front, worth noting. And once again, we have 3 x values. So this is going to look similar to y equals negative x to the third. And from our graphing practice we've done over the past few days, we know the general shape of this is the regular x to the third like we had in number 1, but flipped vertically. So it's going to start here. Right? It's going to start at the top on the left-hand side. That part's going to go to infinity, but the right-hand side goes to negative infinity. So it's the flip version of what we did in number 1. So from here, we know, number 1, the degree is 3, once again. Right? It's the highest exponent. The end behavior, we already know. Okay? The right-hand side, see, as x approaches infinity, f of x approaches, on the right-hand side, negative infinity. Notice how the top line I write is always talking about the right-hand side of the graph, and the bottom line is talking about the other side, the left-hand side. That goes to positive infinity. We can find our zeros. We'll do it without writing it out, so just we can look at here and see that negative 1 will make this 0. 2 minus 2 would make this 0, so 2 is going to be another root, or 0, and 3 will be the third one. We cannot have more than 3 zeros because our degree is 3. That's the highest number of x-intercepts that we can have for any function. We have negative 1, 2, and 3. And from over here, we know the graph will go that way and then go this way. We go to negative infinity that way. And we can still find the y-intercept, right, by plugging in 0 here for x's. So we'll have a negative in the front, 1 times negative 2 times negative 3. So that's positive, let's see here, no, negative 6. We've got negative 1 times negative 2 times negative 3 would be negative 6. So I'd be down here. All right, and then using all the information, we can put together like this. And there we go. There's a sketch. Only thing that's not accurate here is probably this area right here. It might go up more or maybe even less. We can't tell without doing a more precise graphing. All right, hopefully it's starting to make a little more sense. Let's do a few more. Notice how we have an x on the front here. Okay, just treat this right here as an x minus 0, and it behaves the same as all the others. So overall, we have 1, 2, 3, 4, right? 4 x's. So this is going to look similar to y equals x to the fourth. And it's good to know the general shape of an x to the fourth looks like a w. Okay. Crosses the x-axis 1, 2, 3, 4 times. And that's why we have 4 zeros. So we have 0 from x minus 0, negative 3, 2, and negative 7. So we got 4 zeros. And negative 3, positive 2, negative 7. There we go. End behavior, you can see from our graph up here that they both go to positive infinity. They both start and end going upwards. So I know this is going to go this direction and over here this direction. And we can write that out formally. Remember, this part's always the same. Right? And the bottom, this part is always the same. The only thing you need to change from problem to problem is the last two infinities, are they negative infinities or positive? Right? So both of these are positive. Now the y-intercept, you can see that we already have a y-intercept at 0 because that happened to be an x-intercept. So anytime you have an x-intercept of 0, that's also going to be your y-intercept. But if you want to check it, you can still plug 0, let's see here, plug 0 in for x, and you can see y. So if we plug 0 in here, right, the first value we have is 0, and it's going to be times 3 times negative 2 times 7. But the fact that the first value is 0, it's going to be 0 times these numbers. So it has to be 0. 0 times anything is 0. So we don't really need to check it. But anytime you have just an x in the front, that means the y-intercept is going to be 0. All right, so we can go ahead and sketch this. Something like that, right? And again, these are not going to be accurate right here. If you check them on decimals, they might go higher or lower, but for sure they go through these x-intercepts and they do both finish positive infinity. All right, let's actually skip down to how about number 6. So 4 and 5 are very similar, just more practice, but 6 has a square in it, so I want to talk about that. So think of this, if we were going to write it out, this x squared out the long way, it would look like this. X squared is x times x, and then x minus 4 in the end. So what we want to do is look at this, but be thinking this. So if we want to count the degree, we'd count, well, there's 1, 2, 3 x's. So we can see that here, that there's 2 here, 1 here, so our degree is 3. Right? With this negative in front, lets me know it's going to look very similar to negative x to the third, degree 3, with that negative in front. So if we know the general shape of negative x to the third, that looks like this, right? Which starts at positive infinity but ends at negative infinity. We can get the general shape of the graph. So as the right-hand side, as x goes to infinity, f of x approaches negative infinity. Same thing here, x approaches negative infinity, the left-hand side of the graph. F of x, the y values, approach positive, right? So just be thinking that this is the right-hand side, right? Negative infinity, this side's the left. Positive. Right? Just like we did on the last one, if we have an x in front, you'll notice that it also lets us know that the y-intercept is going to be 0. Okay. So we have our zeros from here are 0. And we don't need to write 0 twice, right? So we'll write 0 and 4. So you notice how the degree is 3, but the y-intercept is, the number of zeros is 2. So here we go, let's graph this. So what happens if you have only 2 roots and a third degree polynomial? Right? It still needs to have this end behavior right here. So it still needs to do this and do this. So how do we get from here to here with a cubic equation? Right, that looks something like this. So what we want to do is basically make, instead of going through and making 2 roots, we're just going to go down here and bounce right off and come right up and then back down. Okay. So that's how we can still have the general shape of a cubic function and still get, and only having 2 roots instead of 3. So the reason why I did it here as opposed to bouncing off this one is because there were 2 of them. So the fact that this has 2 that are 0, that's why I bounced off this one and then went through positive 4. And we call that a double root. And a y-intercept is also 0. Anytime an x-intercept is 0, that's also the y-intercept 0. Let's look at a few more that have double roots. So yeah, number 7 has a double root. All right, so we'll do, let's see here. We have a 4th degree, right? We have 2 x's here, and then 3, 4. 2, 3, 4, 4th degree. It's positive in front, so I know in general it's going to look like y equals x to the 4th, which is a W shape. Okay. However, one of them is a double root, right? We have this x plus 1 squared, so -1 is a double root. That's where it's going to bounce off. And then we have +1 and +6 as our other roots. So we have -1, +1, and +6. Our y-intercept, plug in 0 for each of these. Now be careful, well, this doesn't really matter here, but this technically would be 1 times 1 because it's squared, and then -1 and -6. Okay, so 1 times 1 times -1 times -6 is +6. And our end behavior we'll know looks like this, both positive infinity. And it's going to end that direction. We can write that out, both positive infinity. F of x, kind of writing these backwards here. There we go. Positive infinity as x approaches negative infinity. There we go. And now we can graph. Now remember, 1 is the double root. So that's where it's going to bounce off the root as opposed to going through the root. We're going to go here, bounce off the root, go through the y-intercept, go down as much or as little as you want at this point, come back up through the other root. There we go. So again, we go through 1 and 6 here because those are regular roots, and we bounced off -1. We didn't go through it because that's the double root. It has an exponent of 2. So we have a W kind of shaped graph, but it only has 3 x-intercepts. All right, let's do one more. All right, so number 11. So we have another double root here, right? Because we know because it has an exponent. So there's 2 roots of -1, right? We have -1, then we have 2 and -5. Notice I've been going in different orders, so you can start off with the zeros and do the y-intercept, and then do the degree, then do the end behavior. The order here is not very important, so just whatever order you want to go in. Put 0 in here so we can find the y-intercept. So we'll have a negative in front, times 5, times -2, times 1, and times 1, since there's 2 of them. So we'll have, looks like +10 y-intercept. That's way up here. And my roots will be -1 and 2 and -5. So in general, right, we have a 1, 2, 3, 4, 4th degree polynomial. It does have a negative in front, so it's going to resemble y equals -x to the 4th. And look up on your notes, you can see that that shape looks something like this, with both ends finishing at -infinity. And behavior, both of them go to -infinity. As x goes, this is the right-hand side, positive infinity, and then left-hand side, -infinity. There we go. All right, so we have, again, it's going to finish both going down. So we know these should finish both going down. Double root is at -1. go here, go through -5, double root here, bounce off of it. We're going to go all the way up here through our y-intercept and come all the way back down. And there we have our sketch. All right, so hopefully these examples help, and just apply them to the other ones to finish the rest. Okay, good luck.